Yeah, okay, fine. So where we are stopped actually, so we are stopped here. So after we are fixed the root node, so what we have to do further? So further steps where we have to progress, right? So we have to progress wherever we have got the non-homogeneous data sets, right? So non-homogeneous sets, okay, then we have to once again drill it up. Okay, so for that what you have to do, once again, what is the reminding, this outlook is actually it's gone, right? It's already is going to act as a root node. What is the rest of the features? Temperature, humidity, wind. Once again you are going to investigate about the uh, that means it's which one is going to act as a the further investigation. You have to once again calculate the entropy, once again you have to calculate the information, once again you have to calculate the information gain. Based on that you have to take the decision, right? So both the side you have to investigate it, right? So one thing you have to keep it in your mind. Now the total entropy getting varied because how many information is actually coming in this leg? It is sunny, right? So how many sunny is present? 1 2 3 4 5. Only 5 sunny is present. So the total entropy is you have to calculate only for this 5 values. Am I right? That 5 value only it comes here, right? So far you have to calculate a entropy for this sunny, that is going to be act as your total entropy. From that you have to subtract the information gained by your new attributes. So which is you are going to fix it here? Either you may fix the temperature, either you may fix the humidity, either you may fix the wind. Okay, and based on that you further investigation is you have to proceed to build the complete decision tree. Okay, the steps are similar. What we are done here, the steps, everything is similar. One thing you have to keep it in your mind, whenever we calculate a overall entropy, here the overall entropy it depends on the sunny, because this is going to be a entire population for the upcoming uh, nodes, right? So just to take it this one as your complete tree, try to manipulate it. Okay, bring it back this particular structures. Okay. Okay, I hope so. You people are enjoyed this mathematical computation. What is really happening inside in the decision tree? Fine. So I already told so many algorithms are there in the decision tree. We have a ID3 algorithm, we have a C4.5 and C5 algorithms, and also we have a, and just now we are discussing a cart algorithm, right? So in all the algorithm, the steps are similar. Only the slight changes are happened each and every algorithms. ID3 is actually a base algorithm. Okay, whatever we have discussed, the similar steps is actually present in your ID3 algorithm. Only the key point is ID3 algorithm is designed to handle the categorical data sets, right? So that is actually maybe they are considered as a drawback of that particular algorithm. Okay, because nowadays not only categorical data, we are having so many form of data, right? So what C4.5 and C5 algorithm does, it try to discretize the continuous value and make the decision tree is capable enough for the other data type, right? That is a breakthrough given by your C4 and the C4.5 algorithms. And cart algorithm is actually makes the decision tree to works with the regression also. Okay, so many algorithm is actually designed like that. They are used for a classification as well as a regression, right? So in a SVM also, SVM is actually used for a classification as well as the regression applications, right? How it is actually worked in the cart algorithm? The cart algorithm, it gives the decision as well as it try to provide the score value. In the leaf node you get the decision value as well as the score value. That score value is for the prediction value, that is your predicted value. Okay, in such a way it is used for the regression application, right? This is a major difference between this four algorithm and the decision tree, right? And moreover, this decision tree is especially used in the ensemble learning techniques, right? uh, the ensemble learning technique, I can say is that so many weak algorithms or so many weak models are combined together to produce the strong result. Okay, such an algorithm is, we says it as a such a learning is, we called it as a ensemble learning techniques. Okay, why actually I especially connected this particular topic to the decision tree? Most of the time this ensemble learning is actually built with the decision trees. Okay, especially we are using a random forest. Okay, random forest is nothing but it's actually built to n number of decision tree is built for your data set, and we are connected together. That is, we called it as a random forest model, right? So if you are connected like that, what is actually happening? We can easily overcome the overfitting. Okay, that is actually the uh, way of reducing the overfitting, because every model is creating a every model is actually dropping some results, right? Because everyone is actually weak models, not a strong models. So that itself, it creates the, it try to overcome the overfitting conditions, right? I hope so try to you are understand my statements. So this is my decision tree. Likewise, I try to add more trees for my data sets, and takes the voting of the particular models. Based on that, I try to take a decision. Okay, for example, if it is a yes, how many model gives the yes for the same leaf? It's, we are taking the voting of that particular value, then we takes a decision, right? That's why I try to connect this random forest with the decision tree. Yeah, I hope so you enjoyed the decision tree algorithm. So only the two steps. So to build the decision tree, we try to uh, what to say, recursively we have to do the same steps. Okay, that is actually the tedious process in the decision tree. If the features gets increases, that is also one of the drawback in the decision tree. Actually, if we are having a more features, during that time the decision tree is actually creates a more statements, more conditions, right? And another one more thing, whatever we are investigated here, it is actually the univariant decision tree, because in the node we are taken only the one attribute at a time. We are not taken a two attribute. It's simply we are considering it is a mutually that means mutually exclusive features, right? So that's why we are concerned it is a only one feature for the node. If it is a multivariant decision tree, okay, so what happened in the node, we are taking a two features along with the some conditions. Either it may be both are, and they are logically connected, or they may be arithmetically connected, whatever it is. Okay, some conditions we are fixed here with two features. That is, we say it is a multivariant, right? So pruning. So previously we are says what exactly the pruning is very very important while we are concerned with the decision tree. Because if your if your feature is higher, what happen, your tree is also become bulky, right? So many redundant legs may be produced while you are training the model. Okay, fine. So what you have to do, you have to prune such a redundant legs to reduce the complexity of the model. So a decision tree is a graphical representation of all the possible solution to take a decision based on the certain conditions. Am I right? So we have to prune it the unwanted things. We will see that. So look at here. Actually, the previous complete model, we are having a four legs. At finally, we are having a four leaf, right? So what I am going to do now, I just simply prune the no conditions. So this tree is simply gives a, always it gives a yes. Yes is your decisions. Okay. So if this tree is not able to access the yes, means you automatically you takes the condition as no. That's it. This is a way you have to prune the legs. Okay, the tree legs. Okay, we have so many methods to prune this particular decision tree, right? So one thing we have to understand, the pruning is used to reducing the complexity of the model. And moreover, we are not pruned all the legs, we are pruned only the redundant one. So I want to show this particular cheat sheet about the decision tree. Suppose if you are working with the scikit-learn algorithms, so how the scikit-learn algorithms it's actually working. Once if you given a data, whether the data is for classification or a regression, it just the algorithm itself try to identify for this purpose, which means whatever the data we are handling, whether we are going to do a clustering, whether we are going to do a regression, whether we are going to do a classification, we have this algorithm is going to identify what we are going to do now. Okay, because we all know if it is a clustering, that you have to prepare a data set in different manner compared to your classification, am I right? And it is also a different manner compared to a regression. It is also a different manner compared to a dimensionality reductions, am I right? So far, how based on the data itself, how this particular decision is actually this algorithm is going to take, we don't know. Okay, in this case, we are going to apply a decision tree. We takes a decision. Just see how this tree is actually built. Once if we starts the procedure, what happened? It just look at the samples, whether the sample is greater than 50 or lesser than 50. That means the 50 is actually a number. For your understanding purpose, I am keeping it as a 50. You consider a some length of the data. Okay, so here if it is a yes means it going to process, if it is a no means it just give the instruction get more data. Okay, we are decided this is actually the minimum amount of data which is required for all the algorithms. Likewise, we are set the decision here, sorry, set the condition here. So next what happen, it goes to the predicting a category. Okay, whether if it is a yes, do you have a label means it going for a classification application. If you are not having a label, okay, what you have to do, you are going for a regression. It may be for a regression, am I right? Yeah, it takes a decision like that. If it is a predicting a category, yes means next you have to check, do you have a label data? If we are having a label data, we are going for a classification. If you are not having a label data, that means your target value, that is going for the clustering. Okay, next if it is a no, it just coming here, it's predicting a quantity. Okay, if it is a predicting a quantity means yes means it going for a regression application. No means it looking for it keep looking for something, right? So it comes into the keep looking for something. Yes means we are going for a dimensionality reduction, because dimensionality reduction is not suited for this three cases. We are not giving any additional information, we are not nothing we are giving here. Okay, so it just simply give it into the dimensionality reduction process. Okay, so if it is a no means it just predicting the structure. So you are tough luck, we are not identified the proper location. Okay, either a classification or regression or clustering or dimensionality reduction, we are not identified properly, right? This is how the the decision tree is actually we are built it for the real time applications, right? I hope you enjoyed this cheat sheet applications, right? This is how we have to set the potential questions to take a decision, to build a decision tree, right? I want to share another one more point regarding the decision tree, where actually this decision tree is implemented. Okay, in our day-to-day life, where this decision tree is we are seeing. Yes, exactly, each and every day we are actually come across this particular decision tree. Why? Because I am telling like that, in all the customer care calls while we are calling, right? So it actually ask you to it try to retrieve the information from us. So based on the information it takes some decision. If you are if I am calling into the Airtel customer care, what happened, it asks a question like, if it is a Tamil, press 1. If it is a English, press 2. If it is a some other language, it's plus 3. It asks like that, right? You know, if so we are giving the information, what happened, it processed it. So next question it comes. So third question is comes at finally we are reach our appropriate contact person, right? So in all the call recommendation systems are designed with the that particular algorithm, the decision tree algorithm, right? So we have to know what is the advantage and the disadvantage of the decision tree. So decision tree, it generates a understandable rule. That is actually the biggest advantage of the particular algorithm, because it takes the data, it try to process it and it sets the understandable rules. Okay, it is a more generally even human also, it is a understanded the conditions, right? And moreover, the decision tree performs the classification without requiring a much computation. It doesn't compute anything, it doesn't compute any errors or something like that. It simply sets the conditions, that's it, based on the analysis of data. And then the decision tree are capable of handling both a continuous and categorical variable. Just now I said it is used for the cart algorithm is used for both the things, right? And decision tree provides a clear indication of which fields are most important for prediction or classification, because each and every time we are calculating the gain value. Okay, from that we can clearly understood which is actually a most important one. And the disadvantages we can say is because all the algorithm has its own advantage and disadvantage, right? So decision tree is also having the the n number of advantages is there, the same number of disadvantages also there. So it's all based on your data once again. Okay, the machine learning algorithm, if you ask a question which algorithm is actually better or best, so I can say is like none of the algorithm is not good or better or best. It just all depends on your data, how fairly you are collected your data, how fairly you are processing your data. Okay, so decision tree are less appropriate for estimation task, where the goal is to predict the value of a continuous attribute. Okay, the next one is the decision tree. So most of the cases I realized personally from this decision tree, the pruning algorithm is actually, I consider, personally consider, this is actually the drawback of decision trees, because after it forms a tree we have to prune the tree actually, because if you are not pruned that particular tree, definitely the complexity is very high. Moreover, it actually realizes a overfitting condition. That's why that ensemble learning comes into the picture. It try to avoid such a kind of overfitting by making the different tree with the weak models, right? So that's all about your decision tree. Any doubt regarding the decision tree? I hope you people are enjoyed the decision tree. Any doubt? Yeah, here it is actually I placed as a binary tree. Yes or no questions actually. Fine. So the next thing we are going to starts with the SVM. Okay. So after we are completed the SVM, we will try to show the implementation of SVM and your decision tree. Fine. So in the implementation itself, I try to cover the hyperparameter tuning. I hope so. In the name-based classification also, we are discussed about the hyperparameter tuning, because this hyperparameter tuning is actually we have to identify generally what is a hyperparameter, which is much important for your algorithm. Okay, based on that particular value only your algorithm efficiency is going to decides. That parameters is, we say it as a hyperparameter, right? So if you set the parameter properly, you can improve the performance of the model, right? So in that case, I hope so in the implementation session we are discussed about the random search and the grid search. I want to ask one question in that particular point. If you are a person as a beginner, I am going to start algorithm very first time, whether you are go for a random search or grid search, which one is you are opted to set your hyperparameters for your algorithm? Either a grid search or a random search. I hope so you people are know what is actually the grid search and random search. Yes, exactly. So we have to go for a random search. Why? Because we are a beginner. We don't know anything, how to set the limits and all. We don't know how to create a boundary for my hyperparameter. Okay. Because grid search is actually search only within a boundary, right? So as a beginner, we have to follow the random search. From after we are done the random search, we try to identify the boundary, and within the boundary you have to investigate. That is the right option, right? Yeah, fine. Sandhya, are you there?
Oh, yes, I'm sharing my screen. Yes, sir. 2 minutes. Is my screen visible? You should have a slide telling history of SPM. Is my screen visible?
Yes, ma'am.
Yeah. Okay. So, good morning, everyone. So we start with SVM again. So SVM, like most of us are familiar, we have all seen SVM in one way or the other. In like the previous works that we have been doing on, right? So in this session, I'll just quickly walk through what SVM is, like how it evolved, and followed with that, we'll see how SVM differs, or like how SVM stands apart from other machine learning models, and when to use SVM, where to use SVM. Right. So following this, we go with the implementation of SVM. So this is the agenda for today. So as we all know, SVM, it became very popular when it started with the handwritten digits recognition, and it was somewhere around 1992. So considering that let's have a geometrical interpretation of data. When our data is plotted in a manner, when it's distributed in a manner in a two-dimensional plane, what our task as a machine learning engineer is, we'll have to classify our data. So as we all know, classification is nothing but we are trying to fit, or we are trying to draw a line between the two data in such a way that when I have a new test sample, based upon the
Ma'am,
coefficients that, yes,
ma'am,
yes, sir.
ma'am, you are very fast. Speak slowly and in a clear manner. The participant commented, ma'am.
Okay, sir. Okay. Okay. Yeah. So let's consider we've extracted features from our data. Fine. So what do? We just initially, as a initial step, we just plot the data on a scatter plot kind of thing, and we try to see how the data is. Generally, what do we do in all our machine learning approaches? We are trying to draw a classification line, and when we have a new test sample, we'll try to push the sample either to the class 0 or class 1, so that we classify an unknown sample or an unknown test data. So this is our ultimate target in all the machine learning algorithms we have seen. So the same thing also holds with SVM. So when we are given a new data, as a developer, as a machine learning engineer, our target is to draw this new line, right? So in such a way that it classifies class 0 and class 1. So here we are denoting it as +1 and -1. Fine. So this line that we are drawing, it has numerous possible combinations. So either I draw it like this, or either I tilt it like this, or in this manner, or in this manner. So there are numerous possible combinations of how we can draw this line. So our task here is to identify what is the most best fit line. So that line, what we are drawing is going to be a classification line. Fine. So here we might have a question. So this particular line, the drawing the classification line or figuring out the dividing line is done by other algorithms also. Let's consider I have a neural network. So neural network is also trying to do the same thing, correct? So when we give a data, it's trying to make a decision boundary, and that's doing the classification part. The same thing holds with logistic regression, or the same thing holds with, say, some other machine learning model. So how SVM is standing apart from all that is, SVM is not basically trying to draw a line, but rather it is trying to put out a plane itself. So that's why we call it as a hyperplane. So in all the other algorithms, we have only the center black color line that is going to act as a decision boundary, but only SVM will have a margin along with the line. So what do we say margin here? Margin is nothing but two parallel lines along with my decision boundary, and this two parallel line, what we call as margin, is going to run along my complete decision boundary. So from the till the end, from beginning till the end, along with my decision line, there are two lines that is going, that will be my margin. So now how does my SVM classify? It not only depends on the single line, the decision boundary, but rather it's going to have a complete plane along with the margin, so for classification. So this will ensure that SVM is able to perform a better hand than the other classification algorithms when the given problem is very complex. So because we're not going to have one line, but we're going to have a plane itself. So the most good part, or like how SVM gains upper hand than the other classification algorithms, is just because of the plane here. So we have CNN now, we have a lot of classification algorithms now, but still there are certain places which SVM is never been replaced. Even though we have many algorithms being evolved, SVM is still used in them also. Like we have CNN, but still in many cases in CNN also, the last classification part, instead of softmax, in many cases we use SVM. So SVM is found to perform better than the softmax classifier itself. So how it is possible? It's possible only because of this plane, right? So this we call it as a margin. So generally, how do I define my hyperplane? So this is like basic, either for logistic regression or any other model. We can say that our hyperplane is given by sine of wx minus b. So our ultimate motive here is to design a function f. So f such a way that f is a function of x, w, b, where w and b are coefficients that's used to represent a hyperplane, and x is a new test data. So when I get my new test data with respect to w and b, we are going to identify whether it belongs to +1 class or -1 class. So therefore the function f, when it gives the input x, so based on a hyperparameter alpha, which we'll be seeing in future, it's going to give us the y, that whether it says it belongs to positive polarity or the negative polarity. So as we saw, SVM has a margin. Define the margin of a linear classifier as width of the boundary that could be increased before hitting a point. So how we are going to select this margin and what is going to be the width of the margin is what we are going to see in our coming classes, and how it is basically influencing our classification performance. Correct. So there are two cases, as we all know, that I can either there is a maximum margin or either there is a less margin. So now let's go a deeper step again. So what this margin basically does, correct? So let's consider a case. Fine. So let's say 0.5 is a classifying mark. So for example, how many students are passing out in a class? So 50 is a pass mark. So anything like 49 is a fail, and anything like 51 will be a pass. So this is a kind of hard classification that a model performs. But in many cases that's not the case, right? So 49.999 can also be 50. Correct. So this is like a numerical value, but rather considering a complex features in the real time, all our features are not like strictly in such a manner. So therefore there is a need that in terms of classifier, all the features are not going to be a strict in this manner. It's a numerical data, but rather consider data from a real time. Everything is not going to be in this manner. So therefore there is a need that we understand the data in a better manner and do a classification model f, such that it's able to recognize my 0.449 in real time also. So with regard to my real time features, so that identification of my 0.44999 in my real time is also done by this margin. So generally how my other algorithms work, I draw one line, so anything above the line, below the line, it classifies fine, that's it. But what SVM is doing, it's going to draw some margin. So this margin, what it does, it's going to make sure that our two classes stay apart. So why they have to stay apart? We have to make these two classes stay far as possible to ensure that the classification accuracy is very high. So what is the ultimate target? Our classification accuracy should be very good. So making the two classes far apart. So when my yellow color line is increasing, my white color samples and my blue color samples will be forced to move apart. Or we say that my yellow color line should be in such a manner that it is making or it is designing a model that holds my white samples and my blue samples quite far apart. So this will ensure that when I have my new test data, it is able to put it very easily in my whether it belongs to my blue samples or my uh, white samples. So we are all making this with the ultimate motive of generalizing the model very well. So therefore in such a case, maximizing my margin, that is making this yellow color thing in a very high in a larger width, will ensure that our performance with respect to my new unknown sample is going to be very good. So that's what we're going to do. So now how are we going to draw this or how are we going to identify the two yellow color boundary lines or my two margin is what we're going to see. Fine. So the maximum margin linear classifier is the linear classifier with a maximum margin. So it's the simplest one, and that's why it's called a linear SVM. Now all this whatever we are seeing now is with respect to a linear data. So it moves with kernels when we're going to a non-linear data. So when we are drawing this yellow color line, so now our problem comes a deeper step of identifying how to draw these two lines, right? And that is a margin line. So always we'll draw this two margin line on the farthest sample here. So that is, I identify the sample that is farthest from my center line and I fix the sample. Similarly, in both the cases, when we draw two lines along them, these lines will be parallel to my decision boundary, and my sample that we select here, the farthest one, will be called my support vectors. So because these are the vectors, or these are like vectors means we are having a magnitude and we are having a direction too, because it's going to help us identify which angle or in which way the line tilted will give the best classification performance, correct? So there's going to be a direction coming into picture too. So therefore we call them to be vectors. Now why do I call them support vectors? Because these are the vectors that are very crucial and that support our algorithm for the best classification by increasing our width. So that's why these are called support vectors. So support vectors are those data points that the margin pushes against. So it's going to push our margin width. So the maximum margin linear classifier is what we call as the linear SVM, right? So coming into an even better picture, like as we all know, the center line is given as Wx plus b. Now what is our target? Our target is to select a point in such a way that this is going to be the farthest from our given sample, correct? So now making note of the notations, x is going to be my vector, my any test vector, and w is going to be my normal vector. So w is nothing but the vector or the sample that basically my vector that is perpendicular to our decision line, that's the normal one, and b is our scale value bias, right? So now our problem comes even to a deeper level as what is the distance expression for a given point x to the line. So now we are going to identify what is the distance between my given point x and to my decision line, right? So that distance is given by this formula, as we all know, the general addition formula, like the square root of x2 minus x1 plus y2 minus y1, the whole square. Fine. So now the decision boundary should be as far away from the data of both the classes as possible. As we all seen before, now the yellow color margin that we saw previously, or the decision boundary or the margin, is going to make sure that the two classes stay as far as possible, to ensure that when I have my new test data, the model is able to easily make the decision whether it belongs to class 0 or class 1. Right. So our ultimate target is we have to maximize the margin m. the distance between the origin and the line W transpose X is equal to minus B. So therefore now identifying the distance here, so because we'll have to identify the margin distance. Now substituting this formula here, we come to know that a margin is given by M is equal to 2 by norm of W. So identifying, like representing a two margin, we see that our center decision boundary is given by the equation W transpose X plus B is equal to 0. Now the margin that belongs to my positive class is W transpose plus X, W transpose X plus B is equal to 1, and the margin that belongs to my negative class will be W transpose plus X, W transpose X plus B is equal to minus 1. So therefore, this plus 1 and minus 1 is not merely the value that this line is equal to 1, but rather this means that all my samples that come under this class 2, when I add my W transpose X plus B will be equal to 1, and all the samples that I add in this class when I'm substituting the value of X should be equal to minus 1. So it's rather not really the value 1, but rather considering it to be the whole class. Correct? So therefore, our now our problem is even coming narrow. So how we have now come to a even depth understanding that from this equation, right? From the margin equation, we see that the margin has to be very high. When the margin has to be very high, how does it end finally? In such a way that our W should minimize, right? So only when the W is minimizing, or say half, taking this to the taking the reciprocal of it, we get minimizing half of my W norm square will help us maximize the decision boundary. So now our decision boundary is coming to a constrained optimization problem, as my decision should be it should be minimizing my half norm of W square subject to Y into W transpose X plus B should be greater than or equal to 1. So how do we come to this conclusion? Y into W transpose X plus B is with respect to these three equations. So considering these three equations, always, like, my target value Y into the W transpose X plus B should always be greater than or equal to 1. Correct? So let x1 to xn be our data set, and y be our classes. So another one thing with respect to SVM is, here our labels will always be +1 and -1. So the entire SVM itself works with respect to polarity. Like the other classifiers, we have a categorical data like 0 or 1, but rather for SVM, always a positive class will be +1 and a negative class will be -1. So only with this respect to Y we are actually doing the classification inside SVM. Fine. So even when we are doing in a real-time implementation, when let's consider we are, for example, we are doing a cancer detection. So generally, how do we have? We have the malignant cancer and the malignant cancer, right? So in these two, instead of mapping to 0 and 1, when we're implementing SVM from scratch, we'll always map the data to +1 and -1. Right? So the decision boundary should classify all the points correctly. So that is when by having my polarity Y into my W transpose X plus B, so which is nothing but my decision boundary plane, it should always be greater than or equal to 1 for all of my I. Fine. So to see this, when Y is equal to -1, so we're just proving how this comes. Right? So to see this, when Y is equal to -1, we wish that W into X plus B should be lesser than 1. When Y is equal to 1, we wish that W into X plus B is greater than 1. So this is actually a simple calculation. When my Y is negative value, my X will also be negative value, making this condition true. Minus into minus will be plus. When Y is positive value, when X is also positive value, plus into plus will be plus, making this condition true. So for both my negative case and my positive case, my decision boundary will be satisfying this equation. So therefore, from a very big problem, we are now reducing a problem to a constrained optimization problem, where there are only two conditions that we'll have to keep in mind, or that we'll have to consider. First one is minimizing our 1/2 norm square, norm of W square, and second one is all this is subject to my equation W into, so I into W transpose Xi plus B will always be greater than 1 for both my positive polarity samples and my negative polarity samples. Now our condition, or like now our problem comes to solving this two equations. Fine. So how do I solve these two equations? Yesterday we saw in the flowchart that was there, we had a ML model and we had a ML algorithm. So till this now is our ML model. where my W and my B are the coefficients. So these are our trainable parameters and X is our input sample. So yesterday we saw that gradient descent optimization was the widely used ML algorithm for fitting our model, right? As a model was having a coefficients or a trainable parameter, and we used some kind of optimization algorithm that was called the ML algorithm to optimize our or to identify the most effective W and B values. For SVM, we are now initially in the olden days. So first when FCM was proposed, we had something called the dual problem, like we having two problems, right? So this was solved using something called as the convex optimization, using quadratic programming. Why we're using a quadratic programming here? Because our given equation is of the quadratic form, and also we are calling this a dual problem because we're having two conditions that we'll have to satisfy. Fine. So when we are solving the two equations, so our ultimate target here is to identify my W value and identify my B value. Now we have already seen that gradient descent is one way where I fix my W and B value. Apart from this, we have another technique initially that was proposed for SVM, that is my dual problem that we solve with quadratic programming. So what this dual problem is and how it does is what we're going to see now. The new objective function is in terms of alpha I. Fine. So from our previous objective function, using the dual programming, we now solve this, and we are getting a hyperparameter called alpha I. Now it's a function of alpha. The new objective function is a function alpha. It is known as the dual problem. If we know the value of W, we know all alpha I. So if I'm going to know W, we are going to know all the alpha I. If I know all the alpha I, we'll be able to know all the W. So it's kind of vice versa, and that's another one reason why it is called as a dual problem, right? So the original problem is known as the primal problem, and the objective function of the dual problem needs to be maximized. So therefore the dual problem is given by this equation: maximum of W into alpha is equal to summation I is equal to 1 to n alpha I minus 1 by 2 summation I is equal to 1, j is equal to 1 to n alpha I, ji, yi, yj, xi, the whole transpose into xj. Subject to alpha I should always be greater than 0, and alpha I is equal to 1. Alpha I 1 to n, alpha I, ya should be equal to 0. So this kind of solution, or this kind of optimization that we give using the dual problem is called as a primal problem, or we call it a dual problem. So when we're implementing it from scratch, so one condition that we'll be checking is this alpha I should always be greater than or equal to 0. Fine. The result when we differentiate the original Lagrangian with respect to B. So we are obtaining this using the Lagrangian multipliers. Fine. Now, therefore, solving this or doing the solution for this is done using quadratic programming, as we saw. A global maximum of alpha I can always be found, and W can be recovered using the formula W is equal to summation I is equal to 1 to n. Actually, there's a very big derivation behind this and how we are coming to a solution. So which is like it will consume a lot of time. So finally, we are just taking the results alone, and we are seeing in the implementation part there's a library called convex optimization library in Python that will help us do this quadratic programming. We'll see in the implementation part of how our real-time parameters of how our W and the real-time metrics that we use in SVM is mapped to a quadratic programming. So this quadratic programming is nothing but it is a standard set of mathematical models or algorithm that is used for solving the quadratic problem. Like we all know, right? So we have like Cramer's rule for solving a system of equations. Similarly, we have like substitution method for solving algebra equations. Like that, the quadratic programming is a mathematical model that is going to solve our quadratic problem. So that's how our previous dual problem is solved using my quadratic programming. So this is how our SVM was solved in previous days. Fine. Now, how SVM is implemented in gradient descent, we'll be seeing when we are going with the hands-on solution. Fine. So because putting both into the slide part is going to be time consuming. So in this one, we have seen only the primal problem of it. In the hands-on, we'll see with the gradient descent optimization. So how we are taking the cost function and how the cost function is helping us, optimize our W and B value. Now, post this, we'll see how SVM goes for the nonlinear solutions, how SVM behaves when the data is nonlinear, followed with SVM and the comparison with the other classifiers. Fine. So now coming to the characteristics of solution. Many of the alpha are 0 and W is a linear combination of small number of data points. So this sparse representation can be viewed as a data compression as in construction of a KNN classifier. Xi with non-zero is called the support vectors. So as we all know, we had selected some data points to draw the margin. So now the characteristics of alpha I with respect to support vector is found that whenever my xi is non-zero, and those vectors are called the support vector, or we are just mapping how my alpha I will be for the support vectors. Okay? The decision boundary is determined by the support vector, and let Tj j is equal to 1 to s be the indices of the support vector, and we can write W is equal to summation j is equal to 1 to s alpha y x. So it's going to be the product of all the three. For testing a new data, as we all know, the ultimate target is what is going to be my class when I giving my new test data, right? So wherever x comes, we just replace with s, we replace with z. So that's how we compute W transpose z plus b for a new test data. Now therefore a model will now be able to classify whether my given data z belongs to class 1 if the sum is positive, or it belongs to class 0 if a sum is going to be negative, right? So coming to overall picture, coming to overall summation, this is going to be a kind of geometrical interpretation. When we have our data scattered, we'll have a decision boundary, and we'll try to draw another two parallel planes. So these are called as the support vector or the hyperplane. This is going to help us in the decision, and these hyperplanes are opted in such a way that the value of alpha on the hyperplane will not be zero. It will not vanish. The value of alpha will exist. So this is the kind of condition, or this is the kind of value that will help us identify what samples are the support vectors. So now now our ultimate target is I have to draw these two planes, correct? Now, how do I identify? Once we have solved the problem using the quadratic programming, we'll get different value of alpha. Now, from the solution that we have identified or we have obtained from the convex optimization, we will now look out what are the values that alpha does not vanish. For the values that alpha does not become zero, we'll select those values, and those values will be the support vector that will help us in identifying the or that will help us in classifying a new support or new test samples. So after solving using the quadratic programming, we'll identify for which alpha does not become zero. That will be my support vector. Fine. So now, okay, fine. Now, what we have seen till now is like an ideal case, right? Or it's a perfect linear sample. But in real time, most of our data does not behave like this. So very rare case, our data is going to be perfectly linear. In such case, what happens? We are just allowing certain errors in a solution in terms of the ideal case. So instead of ideal case, what do we do? There will be many cases where my blue color sample will be in my that is there will be a positive sample in my negative class, and there will be a negative sample in my positive class, right? So this samples which are in interchanged classes, that is when a positive is in negative and when a negative is in positive, that those samples, correct, which are in the opposite classes will be called as R. Those samples which are there in the opposite classes will be called as a slack variables. So this is how it represents. So we'll be minimizing our summation. Slack variables are represented by this particular notation, by this particular Greek variable psi, and they'll be now our given equation, right? So how the slack variables are introduced into our given hyperplane equation is represented here. So still this now what we are having is a
Hello.
yes, sir, I'm there, sir, I'm there.
Yeah, please.
Um, so support vector should come closer to margin, right? So okay. So now when the slack variables are coming into picture, what happens? A given condition, that's the previous one what we have seen, W transpose X plus B is greater than or equal to 1. That was what we have seen till now, I mean in the previous case. Now with respect to slack variable, we are giving a relaxation condition to our model. So now what happens? Instead of just 1, it becomes 1 minus sigma. So that is that previously it was very hard. That is even though it was 0.44999, my model will still classify it as class 0. That is a fail condition when we are taking with respect to mark, right? When a particular candidate has passed or failed, uh, let's consider 0.5 is our boundary, or it is a threshold. When I give it to a SVM, that was in the previous case where it was perfectly linear. When I'm going to give it to 0.4 999 or 99, whatever it might be, even at that case my SVM will classify it to be class 0. Only when our it crosses 5.50, it's going to be my positive case. That was the previous one. That was the hard classification part. So SVM that is very strict in that we have seen previously is called the hard SVM. But the second case where SVM is that allows a relaxation, where it's having a slack variable introduced, this 1 minus xi, right, that's allowing a slack variable, that one is called the soft SVM, where we are allowing a relaxation, because in real time none of our samples are going to be perfectly linear. It's going to have some relaxation, or it's going to have some misclassified data into it. In order to classify those data also in effective manner, we are introducing the slack variable. So therefore the SVM that is allowing such kind of relaxation is called the soft SVM. So previously, a margin was very hard. We do not allow any misclassification to occur in the decision boundary. Now, in the soft margin, what happens? Any samples. Another particular property of this decision margin or the decision boundary is that inside the margin, we will not be allowing any support vectors. Only with respect to soft margin, there will be some relaxations where I'll be allowing our red samples in a green class. Look, as we can see here, there will be some red samples in our blue class, and there will be some blue samples in our red class. So this way of permitting SVM certain relaxation is what we call as our soft SVM. Now, how do we control the soft SVM and hard SVM? So basically, now again, our system of equation condition was varied, right? So now previously what we had, W transpose X plus B should be greater than or equal to 1. That was a previous condition. Now it changed to 1 minus my slack variable. What happens? We substitute this in our previous equations and we solve for our conditions again. When we're solving for these conditions, we'll get a particular hyperparameter called C, and that C is going to control my width, and also it's going to control my overfitting and underfitting of my SVM. Now that relating my overfitting and underfitting with soft margin, we identify that the soft margin always causes the system to be underfitting, or it makes the system underfitting, whereas a hard margin is always going to make my system overfitting. So therefore there has to be a trade-off between the two: the width of the margin, which is the number of the training errors committed by the linear decision boundary. So these two is going to ensure that my model is going to have an optimal fit, right? So as we've seen, the 1 minus I is going to be a slack variable. My 1 minus I is going to be a slack variable, and we'll have to now a minimization condition becomes so previously our minimization condition was 1 minus 2 norm of W square. With introduction of slack variable, it becomes 1 minus 2 norm square plus C into summation I is equal to 1 to n into psi I. So this is how it varies, and C is going to be the hyperparameter that controls the width of my margin and makes the SVM a hard SVM or soft SVM, right? And subsequently our optimization problem, it becomes this. So minimizing my equation with respect to C, we're going to have a hyperparameter C with slack variable, and also our equation becomes 1 minus my slack variable, where the slack variable is always greater than 0, right? Now, this hyperparameter C is very important for us, right? So C is the hyperparameter which controls the trade-off between the length of the margin and the number of misclassification of the training data. When C is equal to 0, there's not going to be any misclassification. When C is greater than 0, it means no more than C observation can violate the margin. as C increases, the margin width also increases. So the correct value of C is decided by cross validation, and it is the only parameter that can result in the bias variance trade-off in SVM. So as we saw, the soft margin and hard margin is often related to a underfitting and overfitting. Now underfitting and overfitting is always related to a bias variance trade-off. So this indirectly means that C is the parameter that's going to influence the overfitting and underfitting along with our bias variance trade-off. When the value of C is 0, this results in high variance, but when C is equal to infinity, this results in high bias. So therefore, it's very essential that we select an optimal C with our cross-validation techniques. Correct? So far we have only considered large margin classifier with a linear decision boundary. So how do we generalize it when the data becomes nonlinear? Because most of our data in real time is a nonlinear one. So in such case, what we do, whatever we are having, the input space, we are going to map it to a feature space. Now relating this with the first day session that we saw in linear algebra, correct? We were talking about this transformation from one space to another space. Now this SVM is one real-time example where this transformation space plays a very important role with regard to our performance or with regard to our classification in our nonlinear data. So let's consider we have a data like this, where it's not possible to draw one straight line and the data is not linearly separable. So what we do, we are going to map every sample present in our training set using a function psi. So psi of, we are going to transform every sample to another space with psi of all the samples given here. So this is going to be a feature space. So feature space is of higher dimension than the input space in practice. So the computation of feature space can be costly because it's high dimensional, and the feature space is typically infinite dimensional, and the kernel trick comes to rescue, right? So what we are doing, every sample that we had in our training set, we are going to map it to a function psi of x. So that's what we are seeing here. Now we are going to define a function, a kernel function k, given by k of xi comma xj is equal to a function of xi whole transpose function of xj. So the data points is going to appear as an inner product here. So as long we can calculate the inner product in the feature space, we do not need a mapping explicitly. Many geometrical operations, angles and distances can be expressed by our inner product. Fine. So as an example, suppose we're just having a numerical value here of how kernel trick is done. Fine. So now we are going to select some function here, correct? So as we see here, a of my xi comma yj is going to be it's going to do the transformation. So our ultimate target here is to identify some function psi. Now this function psi is going to change our data from a normal space to a feature space. Now how do I select this function psi? Fine. So can I make all the functions that are available to a function psi, or like is there any specific condition that it has to obey? Is what we're going to see below. Is what we're going to see now. So not all my functions can be a kernel function. There's a specific criteria. Only when a condition or only when a function is going to satisfy this criteria, we call that particular function to be a kernel function. Correct? So every function that wants it to be a kernel function should satisfy something called as Mercer function. So only when it's going to satisfy Mercer criteria, we call that function to be a kernel function. Right? Not all similarity measures can be used as a kernel function. However, the kernel function needs to satisfy the Mercer function. That is, the function is a positive definite. This implies that n by n kernel in which I comma jth entry is the ki kj is always positive definite. So what Mercer says is that it should always be a positive definite one. Right? So this also means that the optimization problem can be solved in polynomial time. So there are different kernel functions, like as we saw. Now the next problem comes with identifying what are the different k values. So one particular function is the polynomial kernel, and the next one goes with the radial basis one, then goes with the sigmoid parameter, and so on. So these are the different kernel functions that is helpful in transforming our nonlinear data into a linear one. So the general idea is the original input space can be mapped to some higher dimensional feature space where the training set is separable. So our ultimate target is to draw a linear boundary. Now in my original data, I'm not able to draw my linear boundary. So what I do, my input space, I'm going to map to some feature space phi of x. So this, when I'm mapping it to a higher dimensional space, there I'm going to draw my hyperplane, and there we are going to fit our hyperplane. So that is our ultimate target. And there's a numerical example of how it works. And the same thing we are now seeing it with the QP solver, which is nothing but a quadratic programming solver, right? So these are a commonly used kernel functions and their graphical representation. So this is how a polynomial kernel looks, a radial basis one and a saturating sigmoid. So for example, let's consider these are a few non-linear decision boundaries. In all these cases, we cannot draw a decision one. We cannot draw a straight line. We cannot draw a straight decision boundary. Now what do? We're going to map it to a kernel function one. So when I'm going to map it to a kernel function one, so what happens? Just a minute. It should actually be a GIF file. Just a minute. Participants, is my screen telling SVM non-linearly separable data? Is my screen showing this? Is my screen showing this? Can someone tell on mic? I have not opened the chat window. Is my screen visible?
Yes, ma'am.
Yeah. Okay. So what happens? This is my original data, which is non-linearly separable. When we are mapping it to a higher dimensional plane, so this is what it happens. Now that one we are plotting it to a higher dimensional plane. So now you can see when we are plotting it, it's possible for us to draw a straight line in between the that's in the space in between it. So here you can visualize it very well. We'll be able to draw a straight line here. So this is how mapping it to a higher dimensional kernel works. So as we see here, this is our original nonlinear data. This kernel function is going, let's say radial basis one. It's going to map it to a cone-shaped one, where we're easily able to draw a decision boundary. And similarly here, what we're doing, we are mapping it to a feature space where we're able to draw a decision boundary, right? So this is how. Yeah. Is my screen visible? Hello? No, yeah, just a minute.
No, please. Chandya, no. Oh,
Yes,
okay.
sir, yes, sir.
Now it's coming.
Yes.
Okay.
So basically, we are doing this transformation. So like this, the standard kernel one, the function can also be in the form of like simple mathematical equation where it can be like x square plus y square instead of the kernel one. But only if this is going to satisfy a Mercer function where it's a positive definite, it's going to be it's going to do the transformation for us. Similarly, well, let's say we have a data like this, which is in a 1D form. When we're going to put it in a say like a parabola one, we are able to draw the line. So these are all some of the examples. Now, when we are mapping our nonlinear data to a feature space using the different kernel functions like polynomial, radial basis, and so on. One among them is a polynomial one. So this polynomial feature, as we know, it's similar to how it works in a polynomial regression one, where we are having a polynomial degree. So similar like how in a polynomial regression, the degree was a hyperparameter that controls the performance of the model. Similarly, here the degree plays an important role in controlling the performance here of the SVM2. Like there we use some kind of cross validation technique with a grid search to identify the most optimal degree. Similarly here we can use the same grid search with the cross validation to identify the most optimal degree. The next goes with the RBF kernel. Now here again, like how we had a degree there in polynomial, gamma is important hyperparameter in RBF. So different values of gamma is going to give us a different classification boundary. Depending upon our data, this particular value of gamma can be selected with a grid search and grid search along with a cross validation one. So when gamma parameter is high, the value of kernel function will be less, even for two close by samples, and this may cause a complicated decision. So we have to make sure that it's not very low, it's not very high, but an optimal value depending upon our data set in order to avoid overfitting. Right. So this again a kind of kernel visualization with respect to our cancer classification. So initially it's non-linear one. When we do some kernel transformation, we are able to map it to a higher dimension space where we can draw a decision boundary exactly. Like in this particular portion, you can see we can exactly draw a decision boundary. So this is how the kernel transformation works. Now, how do we choose the optimal kernel function? So again, choosing the optimal kernel function is very tricky. If we are a very expert in our given data, or if you are understood how our data is, we can select the optimal kernel. Say I want sigma, or I want RBF, or I want polynomial kernel. For a beginner, it's always suggested to start with the RBF kernel and start experimenting further. So when we have no idea of how the data is, or when we have no idea of how it's going to be going about, first thing, we have to ensure that the given data is non-linear. After ensuring that the data is non-linear, we start with the RBF kernel, right? So there are different implementations that you can find. Yeah. So we'll just have a quick recap of what are the pros of SVM and what are the cons. So one good thing is that there's always a clear margin of separation between the class because of a decision boundary. That's we're having a margin there. And SVM is more effective when we're having a higher dimensional space. And SVM is effective in cases where the number of dimension is greater than number of sample. Always selecting SVM, or like how do I select for that for a given sample, for a given problem definition that I'll have to go for SVM will depend on these two parameters. That is whether I'm going to whether my given number of dimensions is greater than the number of samples. We'll see it in the coming steps. With respect to these two parameters, that is the number of features and the number of dimensions. Only with respect to these two, we'll be able to identify whether I'll have to opt for SVM or whether I'll have to opt for other classifiers. Fine. And it's relatively very memory efficient. Why do we say so? Ultimately, our target is like, let's consider we are going to deploy it on some edge device. Think of SVM, we only have the support vectors. Only with the help of support vectors, we are able to draw our hyperplane itself. So just imagine how much memory the support vector is going to occupy. It might be very small, right? So therefore, what happens, very little memory consumption is required, and also very little mission cycles will be required while implementing the SVM in edge device. So therefore, it's very effective when we're going to put onto edge computing based solutions. What are the cons? Like it suffers again, this dimensions and the number of features comes into play. It suffers when we increase the number of dimensions. It fails when comparing to other methodologies like decision tree or ensemble tree, right? And SVM is not suitable for very large data sets. It might struggle. And as we all know, SVM works with polarity, -1 and +1. When categorical label comes into picture, it fails again here. SVM does not perform well when the data set has more noise, when it's going to be overlapping. And in case where the number of features for each data point exceeds the training example, SVM will again underperform there. Right. As the support vector classifier works by putting the data points above and below the classification hyperplane, there is no probabilistic explanation here. Like the naive base, we completely rely on the probability, right? But rather here, it's completely based on a geometrical interpretation of the data points. Like how do I arrange my data point, or how are they geometrically distributed? There's no kind of probability coming into picture. So we cannot give a probabilistic explanation of how internally SVM works like the other naive base and so on, right? So where should I opt for SVM and where should I opt for logistic regression, right? So whenever the data is having some kind of geometric relationship, let's consider text. So text, there's always an order of how it comes, right? So he is my classmate. When I say he will always follow is, and this will always follow my, and my will always follow my classmate. That is, a subject follows a predicate, then with an object and so on. So there's always a geometrical relationship of how our data is distributed. So in that case, we'll have to go for SVM. And similarly, let's consider for image also. So as we all know, image is a spatially distributed data, and the spatial relationship is a key factor for all kind of image processing tasks, right? So for these kind of geometrically related data, we always opt for SVM. Whereas when the data is not having any geometrical relationship in it, and when it's going to be completely mutually independent, in those cases, it's good that we go for a logistic regression one. Next, going for when should I go for linear regression? When should I go for SVM? Like both of them are support linear and non-linear, because SVM also we go for kernel trick when we have a non-linear data. Even for linear regression, we go for polynomial regression and so on, and we go for when we have a non-linear data. But how SVM stands apart from linear regression is that SVM is able to handle the outliers in a better manner than linear regression. So both of them perform well when the training data set is less and there are a large number of features. right? So this is the thing. Further, going with logistic regression, SVM can handle a nonlinear solution, whereas logistic regression cannot handle nonlinear solutions. So that we have already seen. Like SVM does nonlinear well, but logistic regression cannot. And linear SVM handles outliers better as it derives a maximum margin solution. So this is what we have been discussing all this while. There's a maximum margin solution that is helping us perform the classification better. Whereas in a logistic regression, it's going to be a single decision boundary. We don't have a margin there, right? And hinge loss in SVM outperforms our log loss in LR. So as we all know, just a minute. So as we all know, log loss is used in a logistic regression, and for SVM we use something called as hinge loss, which we'll have a quick recap in our implementation part. So with regard to our evaluation metric, hinge loss gives us a better understanding or a better error metric when we are evaluating our data than the log loss. So that is one place where SVM gains upper hand than logistic. And when should we use logistic regression and when should we use SVM? With regard to the number of features and with regard to the number of training examples. When n is large, that is when I'm going to have large number of features, and when my total number of training examples is less, then we go for logistic regression. When the total number of features is very high, when the total number of features is very small, but whereas when our m value is intermediate, when the training example is intermediate, we go for SVM. When n is very small and when our training example is very large, at that cases we go for a logistic regression or a SVM with a linear kernel. So this is how our selection of algorithm works. Further, with respect to KNN and SVM, SVM is more complex. As we know, KNN is a very lazy algorithm where it does not even have a training quiz, but rather SVM is very, very complex. Like we have seen how much
Sandhya, a
mathematics.
little bit slow.
Yeah, sir, yeah. Right, we see what's the kind of complex mathematics that goes behind SVM, right? So we saw the quadratic programming, we saw the convex optimization. So it's like a basic understanding. When the kind of mathematics increases, what happens? The algorithm tends to be more complex. When the algorithm tends to be more complex, what happens? SVM becomes capable of handling more complex data than our other algorithms, which are slightly less complex with respect to mathematics. So this complex mathematics behind SVM makes it like a gem, it's like a diamond on the crown, right? So whether with respect to diamond the crown becomes good, or whether with respect to diamond with respect to crown the diamond becomes good. So it's like a vice versa. So it's basically the complex mathematics that's making SVM very strong. And with when compared with decision boundaries are better for categorical data, as we all know, because SVM does not support categorical data, and it deals with collinearity better than SVM. So SVM uses kernel trick to solve the nonlinear problem for the nonlinear data, whereas decision tree derives a hyperrectangle in input space to solve the problem. So that's a okay. So that's a brief introduction about what SVM is. We'll quickly go into the implementation part. Yeah. So participants, there should be a screen which says SVM breast cancer. Just a quick check. Is it visible now? There should be a screen which says roadmap, SVM introduction, reading the dataset, feature engineering. Is it visible? Yeah. So I hope it's visible. So there's a today what are the files that we'll be seeing in SVM? I'll just give you a quick recap, and since we're running short of time, I'll quickly walk through and I'll let you know what are the files that we're going to share today. You guys can have a look at it in the evening or sometime below, and I'll make sure this file reaches you before say 2 o'clock. Okay. So you can just have a look at it because these are self-explanatory, and all the corresponding explanation is given above the line, above the code itself. So you can just check us and let us know, because we still have feature engineering in hold. So I just want to quickly walk through this. So here, what we are seeing in this file specifically is how stochastic gradient descent is useful for our SVM, or how our optimization is done with SVM. So this is about a basic explanation of how SVM works, and this is about the hyperplane, And here we'll be using our breast cancer detection dataset. So I'll just open the dataset for you. So I just want to know, there will be is a screen visible with Excel sheet that shows ID, diagnosis, radius, mean, texture, mean. Is it visible? Okay, so this is the data set that we'll be using for our implementation. It's actually breast cancer data set where we have a different patient ID and whether they are diagnosed for malignant or the cancerous or non-cancerous cells, along with different features like texture, perimeter, smoothness, and so on. So this is the kind of data set that we will be handling today. Okay, so initially we take the data set. As we have seen before, SVM works only on polarity, so +1 or -1, and it's the most important one. Whenever we get our data, we have to always map it to +1 and -1 and make sure that our positive samples and negative samples are mapped in such a way. And we are doing some pre-processing, dropping some unnecessary data, and going with feature engineering. So we are doing the min-max scalar feature engineering here for us to pre-process the data. And depending on your data set, depending on whether you're having a image data or numerical data, your pre-processing might vary. After doing this, we'll split the data to our training samples and test samples. So once that is done, here we are coming to our core part, which is defining the cost function. So as we all know how gradient descent works, right? So there's an objective function, there's a cost function, which we'll be updating to get our function optimized and in order to reach our minimum point, right? So here our objective is, so our cost function is given like J of W is equal to 1 by omega square, sorry, 1 by norm square plus C into 1 by n summation max of 0, 1 minus y into w x plus b. So as we all know, till this equation is what we have seen already, and C was the hyperparameter that controlled our soft margin, our hard SVM margin. So that was the hyperparameter that controlled this. So this is going to be our objective function, and so the same thing can be represented here with respect to lambda, where C is mapped to lambda, right? We are substituting it with respect to lambda. The both thing goes. So the larger lambda gives a wider margin, smaller lambda results in a narrow margin. So for infinitely small, SVM becomes a hard margin. So where lambda is essentially equal to 1 by C. So we have given you the explanation here so that it's self-explanatory and you get to recall this whenever you open the file. And this computing the cost function. So, and this particular code is completely implemented in Scratch. We have not used any sklearn to do this, right? So the here we see the hinge loss given here. So as we've known, hinge loss is nothing but 1 minus the subtraction of the particular value, and this how hinge loss is implemented here. And we see the cost function calculated here. So cost function is equal to 1 by 2 into W into my dot product between W into W plus a hinge loss. So how this is implemented is what is given in the above explanation and the one below here. So as we all know, what do we do for gradient? We take the derivative of it. So derivative of this particular function is given as 1 by n into my W. 2 and 2 will get cancelled when maximum of 0, 1 minus the particular equation and W minus C otherwise. So our next goes with implementing the cost of a gradient, right? So the particular equation given here is implemented here. When it is 0, what happens, and when it is not, what happens. So the implementation part here concerns with the gradient of a cost function, calculating the gradient. Finally, we go into training using a stochastic gradient. So as we have seen, our ultimate objective is to minimize this and maximize the margin and minimize the sum of hinge loss, which maximizes the misclassification error. So we'll have to minimize the loss. So we'll be using a hinge loss here. We'll have to minimize the loss so that we minimize the misclassification. Our ultimate target is to minimize the misclassification. Yeah. So therefore, our gradient is able to reach our global cost minimum. And these are few steps about gradient descent. I believe most of you are familiar with. And this is how a stochastic gradient descent works. We have given the number of epoch and we are finally calculating the ascent. And this is how a weight parameter gets updated. So we are having the learning rate, we are having the ascent, we are having the weights, and therefore we see how the weight parameters are updated. And finally, we call it with a model.fit, which runs the gradient descent. And here we see the stopping criteria. So like this is how the threshold function works, right? So which most of us are familiar with. Based on the cost functions, we'll be setting the stopping criteria. Finally, it goes with testing a model, and few information for your reference we have given here, and it goes with p-value, correlation, and so on. So this is how all the code that we saw on top was how each block is implemented in Scratch, and this goes with the complete code of implementing breast cancer classification using our using our SVM. So as we know, there is a lambda parameter there, right? So that's a hyperparameter, and we can select the hyperparameter using cross validation. So that goes with regularization strength. And since we're using a stochastic gradient descent, we have a learning rate. Epoch is also one of the parameter. You can, if you want, you can modify it. Here it is set at constant. If required, you can modify it too. So these are the hyperparameter that's going to control our performance. And this is how SVM is implemented using stochastic gradient descent. Now, quickly going to the next one. So this is about the same thing, but it's again with the load SVM. I mean, we are using the same breast cancer data set. So there it was an SVM form. Here we're using the inbuilt one that's present inside sklearn. And these are the different features that was there. And here we are doing some more pre-processing to understand the data in a better manner. So we've just given you different forms so that we get to know how the data is pre-processed for before giving to SVM, or how we analyze the data in a better way. And this is about how we take the internal correlation between the features, and we see that which features are highly correlated, right? So we see mean radius and so on. So we see this block of feature compactness, concavity to have a higher correlation, and similarly this block here is found to, the perimeter area is found to have a higher correlation one. Fine. So similarly, we see some plotting with Seaborn. This is about understanding how the data set works. And further, we see some plots to see some more distributions. So we've given this for your reference. And finally, here we apply grid search with PCA to classify it using SVM algorithm. So we apply PCA to reduce the number of features there. Further, we'll be now giving it to SVM for us to do the plot. So where is it? Yeah. So as we all know, I mean, SVM is having we are having a standard scalar. With respect to PCA, we are having the hyperparameter, and since we are using a kernel here, we are identifying the optimal value of gamma using the cross validation. As we have seen already, we can identify the hyperparameters with respect to our kernel with cross validation. We see the implementation part here. And finally, we are calling grid search along with cross validation to identify the best fitting data. Further, we identify what are the best parameters for our SVM with respect to gamma, PCA component, and SVMN. So finally, we plot the confusion matrix along with we plot the decision boundary. So this is how our data is getting classified for cancer and non-cancerous one, right? So just quickly go through. So yeah, so this is the most important part, or like this is about implementing our quadratic programming one into our SVM. So we see that we are having something called the convex optimization library that's used for implementing a quadratic programming. So this is the library that we'll be using, the CVX OPT matrix solvers. And so for linearly separable data, and this is how SVM works. This is a basic thing. And now here, this is the most important part. So as we all know, this is the equation that we'll be minimizing for. And this is the dual problem that we have already seen. So our task here is to map each variable here to the corresponding metric inside our inside the CVX OPT library. So CVX OPT library has certain number of parameters. Now our target is to map each one of them. So how do we map? So this mapping is given here. What PQ is mapped and how do we give the size variation is what we have given here. And this is how the H vector is computed. And here we are calling the CVX OPT library, that is the convex optimization library. So once we have obtained the different data, we have the collection of different data and we'll be giving here. So this is the most important part. So here only we are calling the solvers, like the model.fit here, the quadratic programming in the convex optimizers. So this is what we call for. And when we're calling this, we'll finally obtain the value of the W and B. So ultimate target is to obtain the value of W and B, right? So from the solvers will be returning us alpha, right? We'll be getting the value of alpha. So using alpha, we'll be obtaining the value of W, and we'll be setting the indices S. So this is the value of alpha, and this is the value of W, and this is the value of B that we obtained using quadratic programming that is implemented with CVX OPT library in Python. So following this, we add a middle point. I mean, we do the soft margin thing into it, and we see how similarly it is implemented, right? So the same thing. Finally, this will be the last code that we'll be looking for SVM. So what do we do here? Here we have given two kind of implementation. One is SVM implementation from scratch, and in this code we have given how the kernels are implemented from scratch. So for example, this is the implementation of a Gaussian kernel, and this is the implementation of a polynomial kernel, and this is the implementation of linear kernel. So we are just making sure that it's implemented from scratch for us to have a better understanding of how it works internally, and also to give you upper hand with respect to research perspective. So if you want to modify something internally, say I want to include another parameter into SVM and see how it behaves, so for those cases, like implementation from scratch is very important. So we have made sure that it's available to you post this sessions too. So we've implemented it from scratch. And finally, and this implementation, we are solving it with CVX OPT library that we saw previously with quadratic programming, right? The convex optimization one. And finally, we're calling for the solvers, which we saw previously. So from, as we know, solvers will be returning as alpha. So using alpha, we'll be calculating the value of W and B. So once that is done, we've got it. So this is how it works internally. And finally, we are comparing our performance with the performance of sklearn library. So this is about how it works internally. It's quite self-explanatory. So we have the custom SVM, we have the sklearn SVM, and we are seeing how the performance varies with respect to different value of C and different value of degree. So which is what is given here. So this is how the performance varies with respect to different C and with respect to different gamma value. We actually wanted to have a kind of interactive session, like when C value is 10, when C value is 50, when C value is 100, how it varies. So that's what we actually wanted to do, and that's what we had planned this for. But due to time constraint, we're not able to do it. But however, we are sharing this code with you, so participants, you can just examine how the performance of SVM varies for different value of C, degree gamma, the degree value in case of polynomial kernel, and the gamma function. So that's about SVM. Any queries? Any queries? So I think no queries. So, I think we can start
Yeah.
with
Then
features.
is it any other queries, please? So shall we wind up, please, participants?
Oh my God.
Anything else, Sandhya, you have to say to them?
Sir, we have a small brief about feature engineering, sir. Like that.
Yeah, please go ahead.
Yeah, sir.
Please go ahead within 5 minutes, please.
Yeah, yeah. Suresh, sir, I think you can. I
Yeah.
think you can share your screen.
Yeah. Okay. Fine.
Sir, uniform.
So am I audible, sir? Yeah.
Yes, sir, you're audible. Please continue.
Yeah. Fine.
Participants, actually, due to time constraint, only I actually had to rush up. It's like a topic that we speak for, like it requires a quite long duration, but since due to the kind of topics that we had to cover, we had to rush up. You kindly go through the codes and let me know if any further clarifications are required tomorrow. I'll be having a session tomorrow morning for CNN, so do let me know. You can continue, sir.
Yeah. Fine.
Sandhya and Suresh, you can share your email ID if needed, if possible.
Yeah. Sure, sir.
Sure, sir, sure.
I hope my screen is visible, guys. Screen is visible.
Yes, it's
Yeah, it's
visible. It's
visible.
visible.
Yeah.
It's
Fine.
visible.
Fine. Yeah, actually, feature engineering. I want to share some point about the feature engineering, because feature engineering is it's actually a very important thing while we are working with the ML algorithm. In the starting session itself, we told, whatever we are algorithm creating, that data is very important. So we have to create the data in such a way we can produce the very good response from the, that means we get a very good performance from the ML algorithm, right? So yeah, that means ML model. So here I try to come up with the different feature engineering problems, right? I try to demonstrate all those things. I will share all these files. Okay, so here actually I done with the function mode. Okay, so wherever you want to use this function, you can easily utilize this function, right? So I am not I am not utilized the inbuilt thing. So here I created our own function to do the process, right? So here in the previous slide, actually, she compared the two things, the inbuilt library, the sklearn library, with the, sorry guys, yeah, we are compared the performance with the uh, our custom designed program as well as the sklearn. Why we are compared? Actually, what is the problem here actually arises? Even though if you are creating the same name base by your own, that is your custom program, and also if you compare the performance with the sklearns ahead with the same data. What's the problem? What is the problem arises here? sklearn done the pre-processing properly on the data. Okay, that's why it produces the higher result than our custom program. So we have to understand how to handle the data in better way to produce the great results, right? So here I come up with the actually 7 files I'm going to share. Okay, I will show you the outline of this particular feature engineering. Okay, so what is actually the feature engineering, where it plays a major role? So if you are collecting a data with the features, right? So what is a data set? It's actually a compressed with the different number of features for a different applications. Whenever we are collecting, some of the data is missing. Okay, so handling a missing data, it's actually a very tedious process. So what we have to do during that time, so the data is missed so many reasons. It may be a randomly missing, it may be purposefully missing, because while we are doing a review system analysis, right? The positive review or a negative review analysis, during that time so many people are we are actually hesitate to give the feedbacks, right? So during that time, it's purposefully the data is actually suppressed, right? So far we have to understand at what situation the data is missing. If it is a randomly missing, if it is a purposefully missing, fine. So during that time, what we have to do, so here I actually utilize the 4 different data sets: Titanic data set, Mercadant's Benz data set, and then I used one and all the data set is actually I chosen on the Kaggle competitions. So which is actually highly complex data set. Such a data set only here I demonstrated. So in this Titanic data set, so many data is missing. Okay, so we have to predict the surveillance, whether they are served or not. Okay, it's actually the passenger data set, Titanic passenger data set. So here we have to see what are all the missing datas. Okay, out of the, this is actually our original data set. This is our null values. So look at here, age 177 missing values. So cabin 687 missing values. Embarked is 2 missing values. So one of the simple technique is we simply drop the data. If any data is missing, we simply drop that samples and we are doing our program, right? But that is actually all the time it is not a right choice, because if you drop the values, what happened? The cabin is 687, so your data set is become smaller, right? So what we have to do, two things is possible. One is you try to drop the minimum number of data. If suppose embarked is 2, the only the data which is actually with the embarked is null, that alone you have to drop. Okay, because we are not bothered about the 2 samples, right? So, but the rest of the things, the cabin and age, what you have to do, you have to replace with the either mean value or median value. This is a one of the best way to handle the missing data, right? So far, so here I given the these are all the ways it's actually using to handle the missing data. Here it's actually uh, actually here I given with the situations. Okay, whether it is a randomly missing or whether completely randomly missing or purposefully missing. Okay, so here I explained the situations. Based on that, we are trying to replace the data. So here I write the program, sorry, function which is used to replace the data with the mean values. Okay. So these are all the covered topic here. So where we have to do handle all the cases. One is a mean, median, mode replacement is we have to do, and then random sample imputation is also possible. Some random value is we have to replace instead of replacing a mean, median, mode value. I hope so you people are know what is a mean, median, mode. For example, the salary is we are taken, the salary data, the missing salary information is we are filled with the mean of the all the samples, okay, and the median of all the samples, mode of all the samples. Sometimes we also replace with the random samples, okay. Why? Because if you replace with the median, what happen, the data set getting biased, okay. So during that time, what we have to do, the best one is random sample replacement is best choice. And then we have to capture a NaN value with few features, okay. What are all the new feature is we have to introduce. For example, I can say is wherever that none value is there, you have to create another data with either 0 or 1. That is actually introducing a new feature. Arbitrary imputation, there is a no logic, you just try to place a some point, it's similar to, quite similar to your random sample imputation, right? The another one more thing is the frequent category imputation. So what we have to do frequent category imputation, some of the category is actually repeatedly happened, right? Some of the categorical value which actually repeatedly happen. So by using that category, by using that features, we trying to come up with the new features compared with the missing values, okay. I hope so I'm a little bit fast. Anyhow, fine. It's actually I in this 6 topics actually I covered in this file, okay. So here actually I covered with how to write the functions for replacing with the mean value, it's actually median value. And here I write so after we are replaced, we have to investigate whether the replacement is suitable or not. That is you have to know, right? So whatever the steps I said, you know, here you try to replace it either mean, median, mode, or it is a random samples, whatever it is, but we have to investigate whether our replacement is impacting a impact anything on our data, right? That is we have to know. So during that time, what you have to do, you have to just plot the data distributions. Whatever your data we are having, we just plot the data distribution. Once if you understand the data well, you can easily identify whether our replacement is suitable or not. Let us see here. Actually, I replaced with the median value. Okay, whatever the missing is, actually I replaced with the median value. Look at here. Yeah. So here, yeah, age and the fair is actually I am taken because this two thing is having a more missing values. I try to compare here. 19% of age is actually missing. A fair is actually we are filled, okay. So 0% is missing and survived is also 0% missing. I try to take a age and I try to fill the age and all. So for age filling, so why age is actually missed? While we are collecting a data, um, usually female is hiding their age, right? So it is not randomly missing, it is purposefully missing. So in such a situation, you try to use a median, okay. So this is actually the function, median function. You try to fill the missing data with the median values, okay. So after you are filled the values, what you have to do, you try to calculate the deviations, okay. Try to calculate the deviations. So for why we are calculating all those things, we just have to know how the data is distributed after we are replaced the median value, okay. So for this, actually here I represented the red color indicates our replaced data, whereas our blue color indicates the original data. Look at here, the distribution is somehow it is closer. It is not much deviated, it somehow it is closer. So whenever that missing data is there, if you replace like this, it's not created the great impact, right? It will not change your data set entirely. Am I right? Almost it try to follow the same distributions. This is what we here I proved. So likewise, each and every files here I created like that. What is the need? What is the reason why we need to do all those things? If it is a random sample imputation, what we have to do? I taken here. So once again, I am showing the results. So if it is a random sample imputation, I have to check with the median replacement and the random replacement. The performance is also I shown here. At last, actually, I am showing. Look at here. The blue color, that means the original is actually blue color, median is red color, and yeah, the green is actually random. So if you are replaced with the random, it is not much fitted. but your median replacement, and this is your original data, it is exactly matches. It exactly matches. That's why we can't see the original data. Okay, because I plotted the three things. Okay, our median replacement and your old value is exactly matches. How it exactly matches? What is really happening here? I done some process to match exactly. Okay, I done some process here, and you just see this process. What is really happening to match with our replaced data with the original data? Okay, so here I done that one. You kindly see. You kindly see. Go through this particular file. And this is a arbitrary value imputation. Okay, so based on the investigation of histograms, arbitrarily we are trying to fill the missing data, right? And this is a category imputation. So what are all the things we are seeing here? It's actually missing numerical values. In sometimes in the categorical format also we may missed some of the data. Okay, so that is also here I investigated, and I wrote a depth function for remove the categorical missing data. How to remove the categorical missing data, right? After we are replaced all the values, and this is our this is after we are replaced the values. So most of the cases here also we have to take a mean. Okay, but it is quite different, because in the previous case it is a numeric, we are taken a mean. Okay, fine, we understood the arithmetic mean is a simply added and divided by the total number of data, but here it is something different. Okay, we just kindly go through here how we are taken an average value of the data. So it is simply because of the histogram. Okay, based on the histograms. So look at here, TI is actually higher. So what I am going to do, wherever the data is missing, TI is I am going to replace. Sometimes GD, if it is a random replacement, GD is I am going to replace. This is how I try to identify the frequent pattern in my categorical data. Okay, this is actually handling of categorical data. And this is actually for the encoding. So where we have to use this encoding data and all, whenever we are working with the date and time operations. Okay, during that time we need a one hot encoder, the ordinal number of encodings. Okay, you have so many encoding techniques, one hot encoders, ordinal encoders and all. One hot encoder, it is used in the classification applications most of the cases. For example, I say male and female is missing. Okay, if suppose you are having a data with the gender, okay, male and female, somewhere male and female is missing. What you have to do, you have to identify it, or you have to if you want to encode the data, what you have to do, you simply replace 0 and 1. Some of the algorithm is capable enough to work with only numerical values. Okay, during that time you have to perform the one hot encoding operations, right? And this is for ordinal number of encodings. Okay, this ordinal number of encoding is for data analysis. Whenever we are doing a time and date analysis, during that time we have to do the ordinal encodings. Okay, this is actually the ordinal encoding. What is happening here, I try to take the information past 20 days information. Okay, in that case I fix the numbers for my days. For example, Monday is 1, Tuesday is 2, Thursday is 3. Likewise, I am giving you some orders. This is actually I formed the orders. In such a way, I try to come up with the orders. Okay. So what is really happening in all those cases, guys? The thing is, here we are trying to fill the missing data with our common sense. If we are having a data, if more data is missing in that particular category, or if more data is available in the particular category, we have to understood when we have to place the mean value, when we have to place the median value, when we have to go with the higher random replacement, and when we have to go with the arbitrary replacement. The thing and all we have to understand about the data, then only it comes, right? So for better understanding, I am giving a some of the statement here. So who all are doing a research, you kindly go through all the statements, whatever the conditions I am giving. What is my aim? What is the condition for about this particular missing? if it is the data is missing, this particular data is missing, this is the reason. Likewise, I actually covered all the conditions, okay, and also I covered what is the advantage and disadvantage of doing all those things, okay. Kindly go through it, guys. Sorry, I'm running short of time, that's why
Yes,
I am
please.
unable to
Suresh is
go
already
through all those
110.
things, right? Yeah, sorry, sir.
No problem, no problem.
Fine. So no
Oh,
problem. I try to share all the files to you guys. It's a self-explanatory, and also I shared my mail ID. If you have faced any problem in your research, you just kindly contact me.
so thank you, Suresh and Sandhya, for being with us for the last more than till now. You have been around 7 sessions. You have made it out, and for sincere making an attempt in the last 2 sessions. Everybody should have been got satisfied with your work, and also they got benefited out of your research and the way of work presentations you have done so far. And we thank participants, everybody. We'll meet you again by 2:30, where Suresh Kumar will be talking about IoT data analytics and other areas. So thank you all very much. We'll meet you at 2:30. Thank you, Suresh and Sandhya.
Thank you, sir.